But let us go to our second speaker for our series talk. So this our second speaker is Carlos Henrique de Lima. He's from TRIUMF, Canada. Hello, Carlos. You can unmute yourself and
Yes. Hello.
yeah, thank you so much for agreeing to giving the talk. So yeah, the title of his talk is New Tool to Study Strongly Coupled Gauge Theories. So yeah, we are good to go. So
Yeah, so thank you very much for the opportunity to give a talk here and discuss this ongoing work that I've been doing for the last 3 years, more or less, with Daniel and Yang, where we're exploring this newly proposed direction to study um, strongly coupled gauge theories, more that we really want to try to apply for QCD, but it's a broader kind of tool that can be used for any kind of, not any, but several classes of strongly coupled theories that are really difficult to study otherwise. Uh, so the underlying motivation is that understanding low energy of strongly coupled gauge theories has been a severely difficult problem in theoretical physics. Most of our understanding of QCD doesn't come really from theoretical calculations, but comes from the experimental evidence that can supplement the information to theoretical calculation and vice versa, which means that if you have any other deviations, like any other models that are not QCD but are still strongly coupled, it's really difficult to actually translate the results. Um, so overall, it's a challenging thing to have like a grip on the theoretical population. And the direction that we explore is more or less something that was understood for a while, that if you use supersymmetry, so basically the supersymmetric version of these models have much better theoretical control. You can do much more calculations that you can trust compared to the non-supersymmetric counterparts. But they are different. So you cannot really just get the supersymmetric theory because they have a lot of extra states that you don't want to be present. Uh, but at least is a starting point that is well controlled. And overall, in most of these QCD-like theories, you expect to have the reason that the difficulty occurs is because of confinement. Basically, you have a reorganization of degrees of freedom that you cannot really follow analytically all the way. So you have quarks in the high energy. As you lower the energy scale, eventually you go to a strongly coupled regime, and then you change your degrees of freedom to hadrons, and then they become weakly coupled again. We expect overall to have both confinement and chirosymmetry breaking in this theory, so it would be good if there is a handle to actually try to not only expect but also predict in theories that look like SD. We know that this occurs in our universe, but what if you have a different number of colors, different number of flavors, different groups, and a lot of the challenge is also, for example, some of these strongly coupled theories you can put on lattice, but if you have chiral fermions, it's kind of difficult as well. So even some strongly coupled theories, even lattice cannot really help you with exploring that. So this is the main idea that we aim to explore, which is basically start from a supersymmetric theory and then deform away from the supersymmetric theory in a well-controlled way to obtain useful results for the non-supersymmetric version. This is nothing new. This has been explored in several different ways. There are several different ways to break supersymmetry that can be used to try to get results. But there is an important point that differentiates these different types of calculations is that both the initial theory, so the supersymmetric theory and the non-supersymmetric theory cannot really look too different. Otherwise, it will mean that your SUSY breaking needs to be too large, and then you can quickly lose theoretical control because you're relying on the supersymmetric machinery to do the calculation. So if you can find a QCD-like theory that are not too different from QCD, that's a good starting point. And the other thing is that not all SUSY breakings are created equal as well. Some SUSY breaking are more controlled than others when you have strongly coupled theories because of this reorganization of degrees of freedom. So the breakthrough that happened more or less 4 or 5 years ago was basically the realization that there is one type of SUSY breaking that is well suited for this kind of theories, which is anomaly mediation. So I'll not enter in too much detail about the underlying calculations. You can look on our papers, and I'll show other references that you can look for, but I'll try to more or less motivate why anomaly mediated SUSY breaking is kind of special compared to other types of SUSY breaking. The reason is that the anomaly mediated SUSY breaking is a way to connect the amount of SUSY breaking in your theory to the amount of conformal violation in your theory. And calculating conformal violation in any theory is what is the bread and butter of QFT. So even in a strongly coupled theory, if you have your underlying low energy degrees of freedom, you can construct operators that are violating conformal symmetry. You go to the high energy, you have your quarks and gluons, you can construct the operators there, and then you don't need to know the map of the low energy to the high energy. You can just jump from the low energy to high energy. This is not guaranteed in other types of SUSY breaking. So for example, if you do gauge mediation in the UV, you put your soft breaking parameters in the UV, you don't know exactly how to match them to the low energy. There are some types of SUSY breakings that you have some guidance because of some additional symmetries that you're trying to protect. But anomaly mediation overall, it's kind of a really powerful tool for theories that has this reorganization of degrees of freedom. So we can start in the high energy where everything is perturbative. We have your quarks and gluons, and then you put your anomaly mediation, and then you can see that there is a limit of the SUSY breaking that goes to something that looks like QCD, and you're happy. And then you go to the low energy, and you know exactly how your hadrons and mesons are going to interact with, or are going to be modified by your SUSY breaking. So I mentioned this is recent kind of progress. This was motivated by Hitoshi. So 4 years ago, he pointed out that this can be used for QCD-like theories to try to obtain more theoretical results. And this basically opened the floodgate to apply for any type of strongly coupled theory. So far, basically, the literature has been applying this tool everywhere that you can do. So now we have basically a hammer and everything is a nail. And then I'll highlight these 2 recent works of mine where we are not really trying to understand generic strongly coupled theories. You can have some motivation to do that because there may be some interesting phenomenology for example, dark matter sectors that you have a little bit more calculation that you can trust compared to just using your SC3 and then rescaling stuff. But we really want to try to connect as close as possible to QCD, especially this last work where we're trying to go to baryon dense environments where, in principle, we have a way to calculate things that nobody else can. So let's highlight more or less how the procedure to apply this to QCD is and why we choose the specific theories that we choose to try to connect closer to QCD. So the starting point is the supersymmetric theory. So you have quarks, gluons, S-quarks, and gluinus. We in principle start with SUN, but eventually, because we want to match to QCD and try to connect as close as possible, we fit follows to 3. Why the supersymmetric theory is so well controlled is because the SUSY structure allows to have some really good control of the low energy descriptions of these theories, even when you have confinement because of the Steinberg duality. So basically, in these theories, you have 2 ways to describe the same theory. And the important point is that outside of the conformal window, which is more or less where we want to be, this duality describes a strong weak duality. So when quarks and gluons are strongly coupled, hadrons and baryons are weakly coupled, and vice versa, which means that we almost can describe the whole theory. There is still a region around the confinement scale where both descriptions are becoming strongly coupled that we cannot match. But again, if you go back to the anomaly mediation, the reason why anomaly mediation is so good, we don't really need to describe the region to have information of both the deep IR and deep UV. This is another important point that I mentioned about how can these tools be useful. The starting point cannot really be too different. And if you ever study supersymmetric QCD, you know that depending on the number of flavor, things can look extraordinarily different. So basically, if you have 2 flavors to 3 flavors, the theory is completely different, which means that you have to be careful of choosing a flavor if you want to recover QCD results. Thankfully, there is a number of flavors in relation to colors that the initial theory of supersymmetric QCD is really similar to QCD. There's still additional degrees of freedom, but the dynamics, underlying dynamics is not so different, which is when you have S confining, which is basically having a number of flavors, one more than number of colors. Why this looks like QCD is because in the high energy, again, gluons, quarks, S quarks and gluinos. In the low energies, because of the Simon duality, you match to only baryons and mesons and S baryons and mesinos. So basically, you have a completely confining theory. You don't have extra gauge bosons lying around in the low energy. You have a vacuum. This is also something that is not taken for granted. You have a vacuum. But at the same time, this theory doesn't have chiral symmetry breaking. And we expect QCD to have chiral symmetry breaking. So once you do this matching of the Simon duality as well, it is not guaranteed that you're going to know all the constants that appear. Basically, because you're jumping from the high energy to the low energy, there may be some unknown coefficients that in principle are calculable because everything in your SQCD should depend only on the gauge coupling or in the confinement scale. But because you have to do the jump, there's some unknown coefficients that we classify them, for example, here in our superpotential, we have the low energy constant that in principle, we don't know exactly the value of them, but you can still say something about the underlying theory if you try to explore all possibilities of these kappas and lambdas for this case. So in this case, you don't generate that many free parameters once you play this game. You only have 2 to have worry about. So what happens once you actually put anomaly mediation? I mentioned the starting point doesn't have chiral symmetry breaking, and we expect chiral symmetry breaking the non-supersymmetric theory. And this is what we see as soon as we turn on anomaly mediation. So in the UV, you see that the partners of the quarks and gluons are getting heavy as you increase the SUSY breaking parameter, which is what you want to expect because you want to actually go to the QCD regime. You jump to the low energy, and then you see that SUSY breaking induces chiral symmetry breaking. And more importantly, the result that we show is that it is independent on the size of the SUSY breaking, actually, which means that if the theory, if for any value of the SUSY breaking parameter, as long as non-zero, you break chiral symmetry breaking, you expect that as you turn on the SUSY breaking or lower, you don't really expect to change. Which means that it is likely that once you go to the exact non-supersymmetric limit, this gets preserved. The calculation that we did here is for all colors and flavors that preserve this relation, but then we end up focusing more in the 3 colors and 4 flavors. The plots, you can see that in principle, there's still 2 unknown coefficients, but you can still be guided by some underlying properties like perturbativity, for example. You know that the low energies, your hadrons and baryons better be perturbative, otherwise you shouldn't be describing their interactions. And once you do this restriction that you see that your couplings, for example, this kappa here is heavily constrained by perturbativity, and you're leaving around the chiral symmetry breaking regime. You never are in a regime where you don't have chiral symmetry breaking. One thing that we also wanted to check is just for the robustness of the calculation is like, okay, what if you put higher order corrections? Can these things break down? Because you always have to be worried. If strongly coupled theories, it could be that you actually are in a regime that is non-perturbative. The only way to know is actually to go to the next order. And we did that when we saw that it's mostly insensitive to high order corrections, which is so far nice. So basically, so far we were able to show that this theory that looks similar to QCD, you still have 4 massless flavors, which is something that is really difficult to calculate otherwise in other methods. But you have 4 massless flavors, which doesn't describe a universe. This is a problem that we're gonna address shortly. But you can show that this theory is breaking chirosymmetry, breaking as soon as you start to approach the non-supersymmetric limit. After we got this result, we got together to try to think about, like, okay, what else can we learn using anomaly mediation? What else it would be interesting to see in to try to understand for a QCD-like theories that we cannot do otherwise. This is where we started to try to explore the phase diagrams. The phase diagrams for QCD has been an incredibly challenging endeavor to explore theoretically, again, because of confinement, because you can describe in the quark phase, but you cannot really describe the region around nuclear matter. But in principle, in our approach, somehow this region below the confinement scale, everything is so much more well controlled. In some sense, the supersymmetry, even with SUSY breaking, restricts a lot the form of our kind of chiral perturbation theory. And because our starting point already have baryons and mesos, they are already present on our chiral perturbation theory differently than once you actually play this game in real QCD. So then we wanted to find out, okay, once you put finite density or a finite temperature, what happens? You have to be careful because both of these things break supersymmetry. So again, you always have to have some perturbative control of these parameters. You never can explicitly put them to infinity, but then as long as they are below the QCD scale, you should expect that things are well controlled. I'll show mostly results about chemical potential. We are currently doing the temperature calculation, which has some additional challenges that I may talk by the end. But with the chemical potential, we already got some really interesting results. So just some details is that differently than the just regular zero chemical potential, zero temperature, where everything is well behaved, once you put a chemical potential, the supersymmetric theory eventually becomes unstable. This is a bad sign because if you go back to what I mentioned, that the supersymmetric theory better not be too different than a non-supersymmetric theory. If the starting point is unstable, this highlights there is some higher sensitivity on the strong dynamics. And we showcases that this is kind of what happens because this instability can be stabilized by strong dynamics, but only if you have SUSY breaking. But this also highlights that there is a little bit more sensitivity on the low energy constants that we cannot access. Just for some calculation information, basically the way that we did the baryon chemical potential, and that's why it's necessarily not so difficult to do it, is because you can also introduce in a Spurian way in the supersymmetry. So you just in the same way that a normal chemical potential can be thought about the time component of a gauge field, you do the same thing for the SUSY. Everything just becomes super, but then you have still some nice theoretical control. Once this problem is addressed, and this is really a big problem because the stabilization depends on strong dynamics, there are some low energy constants that we don't have access to that needs to satisfy some conditions to be sure that things are stabilized. And we don't have other ways to know to calculate this kind of models otherwise. So this is a really important limitation, but at the same time, if gets stabilized, this is kind of the only way to stabilize in a perturbative setting. this is more or less how the stabilization works. The stabilization works is because you have to go to your next leading order in your chiral perturbation theory. In the supersymmetric version, it's basically next leading order on the color potential. These operators are generated by QCD itself, so there is not that we are introducing new physics in UV and the deformity theory away. The UV is still completely just QCD, but as your theory approaches the QCD scale, you should expect more and more higher dimension operators to appear. In supersymmetry, this gets a little bit more restricted because you don't generate superpotentials, but you generate kinetic renormalizations, which is this object. But at the same time, before we only had 2 free parameters, but now we introduce 5 more or 6 more. And you have to keep track of them because we don't have a match to experiments, which is the main challenging of trying to do calculations that are not exactly QCD. But then the approach that we try to do is just figure out, okay, you just do some random scans, which symmetry breaking partners are we seeing? Are we seeing something interesting? Are we seeing not something interesting? And try to map out the possibilities, assuming some kind of naturalness where all of these couplings are more or less of the same order. And sometimes you only turn on the couplings that are more sensitive to the actual stabilization. And playing this game, we were able to find out some really interesting dynamics. So basically, the first 2 points there are the unbroken symmetry group. I mentioned we start with chiral fermions, so we have the whole SU4 cross SU4 symmetry. We also have the chiral symmetry breaking vacuum in the zero chemical potential once you have anomaly mediation. But then we identify 3 other vacuums that some are normal looking, some are really strange and exotic. So you have something that is a version of a chiral symmetry breaking vacuum, but with a smaller group, and the baryon number is spontaneously broken, but there is a residual group that is preserved. Then you also have this kind of models where you have symmetry breaking partners that you have chiral symmetry breaking. You have baryon number spontaneously broken, and you also have some residual SU3 kind of structure. So just to highlight how these things look in the parameter space, we did several scans assuming different kinds of scalings for these couplings. It is challenging to try to draw any conclusions because you don't know exactly the couplings and also the relations of the couplings. This is something that we've been trying to work to try to connect more with real low energy constants. But so far, the game that we play is try to plot on M3 halves to chemical potential plot, and you should think that you want to increase as further as possible the SUSY breaking. So you should think that SUSY breaking is just one final slice that you should be thinking about. And then this relation here, we fix the couplings, this all the low energy couplings to preserve the MDA scaling. This is slightly problematic because MDA also assumes strongly coupled, so we have to restrict the coupling to be really small for to be able to have still perturbative calculations. And then the difference between the plot on the left and the plot on the right is that we, in one of them, we only turn on the importer coefficient for the stabilization versus turning on all couplings more or less with the same size. And you can see that you have kind of like, this is the expected behavior that you see in this series, that you start from a chiral symmetry breaking vacuum as you increase SUSY breaking, and then you transition to a spontaneously baryon number breaking vacuum. But it's still in the, if you go to our real world, it's kind of still in the nuclear matter kind of phase. We can also play this game with different kinds of slices in the parameter space, and all of them more or less showcases this feature that as you increase the SUSY breaking, you eventually goes from chiral symmetry breaking to some exotic phase. Exactly which exotic phase you go is unclear because you don't know exactly the parameters that you're going, but all of them are spontaneously breaking the baryon number in some way or another. And all of them are in the region where we have zero theoretical control. This is the nuclear matter region. We are below QCD scale for these densities. And this is basically the one of the few ways that we can actually try to explore these regions. It's still a little bit unsatisfactory because we cannot really pinpoint exactly what is the couplings that we should be thinking, because you should think that there is only one point on this selection plot that describes the real QCD, because all low energy couplings are fixed by the QCD scale or by the gauge coupling. But at least you can have some more qualitative descriptions of what you expect of these transitions to go to these non-standard phases. One thing also that we highlight that is possible to calculate in these scenarios is the type of transition. So we're able to pinpoint that some transitions are first order, some transitions are second orders. Again, still completely dependent on the coupling values, but we also notice that some vacua, the transition always seems to be first order, the other always seems to be second order, but you still don't know exactly which slice of parameter you're living in. But this is also something that can be used not only for QCD, but if you want to do some model building a little bit more precise, you can try to use this kind of calculations for example, for dark matter strongly coupled secluded sectors to describe some of these transitions inside, which is at least you have a little bit more theoretical control compared to just relying on rescaling some lattice results. So I'll reach my conclusions. So I'll say that this approach can be used not only for QCD, but the thing that really motivated us is try to get as close as possible to QCD. And once you apply that for S-confining theories, we see that SUSY breaking induces chiral symmetry breaking. And as you go to the finite chemical potential, you see exotic phases that some of them have a similar counterpart in the real world, like once you have isospin breaking inside heavy nuclei, for example. But because we can do the calculation with 4 flavors, but we cannot do with 3, it becomes slightly more difficult to actually match exactly to QCD. This is something that we've been working on, how to have this in a controlled way. Another approach that we've been trying to explore is to go to the nuclear theory of this kind of theories, because one thing is to show chiral symmetry breaking, but this can be more universal feature of this kind of strongly coupled theories. But what about the underlying interactions? Are these mesons and baryons binding as well? Or this theory only looks like QCD, but the underlying properties are really far away from QCD once you have a small SUSY breaking. We are right now doing the finite temperature calculation. The calculation is so much more intricate because there is no spurion formalism, because the spurion version of finite temperature is geometrization, and the geometric picture of finite temperature is tricky once you put supersymmetry, because it breaks supersymmetry especially. But we've been having some preliminary results about how you can have chiral symmetry restoration and so on. So keep a look on that. It should be on arXiv in the next month. One thing that I want to reinforce is that even when SUSY breaking is not infinite, which is when you don't reach completely the non-SUSY result, this is still a strongly coupled theory that is calculable, both in the low energy and the high energy, with a theoretical control that is better matched than just normal chiral EFT. So this is already something. It's not the perfect, but it's slightly better and more controlled that we can do otherwise. And this whole area is trying to reinforce this thing that supersymmetry doesn't need to appear on colliders. We could be living in a world that is not supersymmetric, but it can still be useful to understand physical systems, even if they're not supersymmetric. So with that, we end up a little bit early, but we can ask for questions. Thank you.